it's time to look at our last type of generic surface. We've looked at planes and we've looked at cylinders. And the last type is called a quadric surface. It's a graph in the equation form ax squared plus bx or by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus a constant is equal to 0. All right, so that's a lot going on, but what happens in practice is that some of these terms can be combined with, say, completing the square, and you can make it look more generic, right? The most easy form of looking at these is in this form, right? So this is the generic quadric surface form. And as I was saying, you can simplify that first form often by shifting around and fiddling with some algebra to make it look like one of the simpler forms. And then the next page contains a table that identifies those different types of quadric surface in their simplest forms. So to graph a quadric surface, what you do is complete the square. See, some algebra will be involved. So you complete the square if necessary. To identify the shifts. You use the table provided, and that is on your exam notes packet as well, that table. But of course, you also can graph them in Maple. You identify the type of surface you'll be graphing and the orientation of that surface. And then you use the traces in the coordinate plane to help you draw the graph. So in the XY plane, you have an XY trace. In the the XZ plane, you have the XZ trace. And then where that surface intersects the YZ plane is called the YZ trace. So in other words, if you're on the XY plane, that would mean that Z is equal to 0, right? So Z is equal to 0, what would it look like for that surface to intersect that XY plane? We've already seen this type of or comment about traces back in a few pages ago when we were graphing those planes, right? So when we had that plane that we were graphing, we had traces where it was cutting across the particular planes that we were looking at, right? So if you remember, you have an XZ trace, an XY trace, and a YZ trace. Oops, I should have said trace. I just see the typo right there. So I should have said trace. Right? It's where it intersects the YZ plane. So for the YZ trace, which is what we were just looking at and what I just fixed, that would be x is equal to 0. All right, now let's look at the table. And again, this is given to you on your exam notes packets. You don't really have to memorize them. And moreover, you can draw them in Maple, so it's not exactly, hard to find. So you have traces. So if you think about if I intersect this particular ellipsoid, that's what this is called. It's like an egg shape, right? So if you intersect with this plane, you're going to get an ellipse. If you go with this plane across, you're going to get an ellipse, right? And then let's see, that was the XZ trace, and then the XY trace, and then there's the YZ trace in the back, which is kind of going up and around, right? So every time you intersect it, all the traces are ellipses, right? So every single one of the plane intersecting with that ellipsoid will cause an ellipse trace. Now, an elliptic paraboloid has it so that you have parabolas, hence the name paraboloid, on two of them, right? So you have one here and you have one here, right? Those are parabolas. And then if you intersect it across a z value, it goes like this. And actually, this bears commenting. This whole table assumes that everything is open with respect to the z-axis. That does not have to be the case. So do you see how it's z equals x squared over a squared plus y squared over b squared? That's why it's opening in the z direction. So we better make a note at the top, because these are just standard forms, but you could write them in another way. So this table assumes that all graphs open with respect to the z-axis. In other words, they're vertically oriented. Now, let me give you another example down here. If I had y equals x squared over a squared plus z squared over b squared, that would have the paraboloid go a different direction, right? So instead of opening in the Z, it would open in the Y. It would go like this. I have to draw this very carefully, right? It'd go that way, right? So you'd have this shape and you'd have this opening in that direction, right? It'd be taking this and tilting it, right? So just keep in mind that the way this table was set up was assuming a vertical orientation, but they would all work with other orientations as well. Now, grant you, the ellipsoid is actually the same no matter which way you rotate it. So this one would actually be the same no matter what. But this one you could change to have it open in the y direction or open in the x direction or open in the z direction. If you want to open the x direction, it'd be x equals y squared over a squared plus z squared over b squared. And it would come out at you like this, right? It's like a vase on its side. Again, I'm not a perfect drawer, but just imagine this curve kind of drawn. Take this whole vase, this bowl, and tilt it so that the opening, instead of being up here, is over here on the x-axis. And I can do that with any one of these. So if I look at the next one, this is a hyperboloid of one sheet, right? So when the traces on these axes are hyperbolas, you can see, hello, that's a hyperbola right there. And then there's another one right here, which is kind of harder to see, but it's going right there, right? And then it's, if I cut it across a z-plane, a horizontal, then it makes a little waist. It's got like a little ellipse going like that. But again, it's open in the z direction because it's minus right there. If I made it open in the y direction, it'd be x squared over a squared plus z squared over b squared minus y squared over c squared equals 1. And that would make it, well, here, hourglass shape, but kind of doing it that way instead, right? Well, I'd have to do it like that, right? It would make it open up on the y-axis instead. And again, you could do one with the x as well. All right, a hyperboloid of two sheets has a hyperbolas again that are traces, but they're separated, right? So there's a gap in between. So it's like you take the pieces of this and you stretch them out, right? And again, when you're cutting across, you're going to have ellipses, right? So there's an ellipse right here if you hack into that, right? When you cut across it, it's an ellipse. Oops, it should go to the edges. Sorry about that. Right, when you cut across it, it's an ellipse, but this piece right here, that's a hyperboloid, and so would be its companion, although it's hard to draw in the x-plane, or xz plane, I should say. All right, then this is an elliptical cone. Oh, and as per usual, it's opening in the z direction because z is the only one that's positive. If you want to open it in the y direction, just as an example, you go negative y squared over a squared minus, oh no, sorry, I want to do the y direction. So negative x squared over a squared minus z squared over c squared plus y squared over b squared. The one that's positive is going to be the direction you're opening in. So again, it would do something like this. Have a bowl over here, and then have a bowl over here. Like that. I'm not drawing it well, but you get what the gist. All right, and then elliptical cone, it's opening in the z direction because z is the one that's over here by itself, right? So if you have traces, right, it makes the traces and the x equals x naught and y equals y naught are hyperbolas or intersecting lines. So it makes either a hyperbola if you're hitting the curvy part or a straight line if you're hitting straight across like that. And then if you hit the curve part, it actually makes like a curve. And then over here, if you hit it this way, then you're getting an ellipse, right? So that's a cone, right? It's like a hyperboloid of two sheets, but it actually comes together in straight lines at the edges. So that's an elliptical cone. And just for more fun, I'll just do x squared over a squared plus z squared over c squared equals y squared over b squared. And that would be like this. Like that, right? It'd be a sideways cone instead of an up and down cone, right? And again, all of these have companions in the x's. I'm not even bothering. I mean, I could, but all of them, this one would have a minus x squared over a squared equals 1. So this would be y squared over b squared plus z squared over c squared. And the only negative one would be x. This one would have negative or negative y, negative z, and the only one that's positive is an x, right? And then, well, actually, I'll just write that in. Give me 1 second. There. So those are how you would write them if you wanted the x direction, right? And I've written the red ones are y. And then I'm not going to give you all of these on the table. So the bare table just has the ones that are typed and printed, and that's on your note sheet. The trick is to recognize, oh, there's a pattern here. And so that pattern will hold true even if it's opening and orienting itself in a different direction. Now the last one is a fun one. It's the hyperbolic paraboloid. It's a saddle shape, right? Which I really love. Saddle shapes are really fun because if you intersect one way, it's a parabola, and then another way, it's kind of hard to see, but there's like a downward parabola this way, upward parabola this way, and they're oriented at 90 degrees from each other. And then if you go a different direction, there's hyperbolas, right? So along the z equals z0. So it's a little hard to see, but it's like going in and going in like that. Those are hyperbolas. So it's really fun. It's a Pringle shape, if you've ever seen a Pringle chip. So Pringle chip or a saddle. So feel free to go buy some Pringles. And it's for the fun of it. And again, of course, this one's oriented in a particular way. You could make one oriented with y equals x squared over a squared minus z squared over c squared. That would work. Or you could make one oriented a different way, which would be x equals, let's see, y squared over b squared minus z squared over c squared. So those would be the companions. So recognize that this table is giving you these general types, but there are other general types. The whole table is assuming everything is opening and with vertical orientation with respect to the z-axis. But there, for every single one of them, except for the ellipsoid, because the ellipsoid is always closed, so it doesn't really have an orientation. But for all these other ones, there's an orientation to it, and there's always two other ones that are not typed, that are just as valid as the one that is typed. All right, so let's practice, at least first couple. Okay, we want to identify the surface here. So I'm going to keep that table handy so I can refer back to it. But and any orientation and shifts and all of that good stuff. Okay, so if you'll notice, one of the things that's true about all of these, they're either equal to 1 or they're equal to one of the variables, right? So I can see all of that. So I'm going to try some algebra here to manipulate this. I'm going to try dividing everything by 16, because why not? That would turn it into x squared over 4 squared plus y squared over 4 squared minus, well, see, 4 goes into 16, 4. So that's z squared over 2 squared equals 1. Let's go back to our sheet, shall we? Okay, so it is fitting into this pattern right here. See it? Right? So I even wrote it that way. 4 squared, 2 squared. So you can see it. Nice. Okay, so this is a hyperboloid of one sheet. So let me write that because it wants to know what's the quadratic surface. So the surface is a hyperboloid of one sheet. Okay. Now, it also wants to know the name and wants to know the orientation and any shifts. Well, it wasn't really shifted any particular way. Shifting, of course, remember, happens when you have like x minus 3 squared or something like that, and we don't have that here. So there was no shifting, and it's oriented in the vertical axis, so it has a vertical orientation. Oh, let me just say that, vertical orientation. Which means it opens up on the x-axis. Or, it's me, with the z-axis. Oh my goodness. I knew what I was going to say and I couldn't say it. All right, so let's see here. When z is equal to 2, let me see here. If these two are both zeros, then that would be 4 squared over 4 squared. So I would hit at 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right? All right, so it's going to do something like I mean, it's going to make kind of a waist this way, and then you're going to kind of go vertically like this, right? It's a vertical hyperboloid of one sheet. Now, of course, we are terrible drawers, so we are going to make Maple do this. Please, goodness, let's make Maple do this. And I want you to notice there's actually a couple ways I could have done this particular one. Now, I did a plot 3D and I did an implicit plot 3D, and one of these is obviously better than the other. The thing about plot 3D is it actually has to be solved for z equals. So you have to take your equation that was given. You have to solve it for z, which of course it's a z squared. So it's 4z squared equals 16 minus x squared minus y squared, divide by -4, and then you have to do plus or minus, which is why when I'm graphing it, I'm actually graphing a positive and a negative. And you can see it actually gives you this huge gap in the middle. It's just awful. But nevertheless, I wanted you to know that you can play with plot 3D, but it's not something we do very often because we often don't have these solved for z. And it is automatically z, right? Plot 3D is z equals. So all you're typing in is the f of x, y right here. Okay, well, that's awful. So let's use the implicit plot 3D. If we just type what was given to us right there, and I pick -8 to 8, -8 to 8, and so on. And if you don't like the fact that you can't see the axes, you can just add a transparency coefficient to this. I'm going to put in 0.2, for example. And then you'll be able to see your axes kind of poking through. There it is. So it's a hyperboloid of one sheet. Simple as that. And you can see I was right. Look, it's hitting at 4 and -4 right there. And it's hitting at 4 and -4. And if you cut across it on a vertical plane, a z equals a number plane, it makes an ellipse, right? It's got a little waist to it. It looks a little bit like a corset from back in the day. All right, so that's that one. All right, now what about this one? And of course, why don't we just graph all of these in Maple? Well, of course you can, but you're trying to get a sense of what these look like without Maple, and then you can use Maple to back yourself up because these are standard type surfaces. These are not, really funky ones. So we're going to want to kind of know them instinctually a little bit. All right, so I see 4x minus y minus z squared. Okay, I notice that I have a letter by itself. So when I go to look at the list, I'm noticing that one has a letter by itself. And so does the bottom one, right? So I'm going to solve for that letter by itself because everything else has those things squared. So let's see here. I'm going to add y squared, add z squared. Just do a little bit of algebra here. 4x equals y squared plus z squared. So x equals y squared over 4 plus z squared over 4, right? Because you divide everything by 4. Right? Well then, that, because there's a plus, right? If there was a minus, it would be this one down here. But since there's a plus, it's this one right here. But notice it's this one, right? It's oriented in the x-axis direction, not the z-axis direction. See? So this is an elliptic paraboloid. Oh, that's the surface. I'll put that right there. Elliptic paraboloid, which I always think looks a little like a vase. Okay. And now its orientation, it hasn't been shifted. There's no like y minus 2 squared or anything. So there's no shifting again. That'll go away in a little bit. But there's no shifting. It'll go away the next problem, as a matter of fact. But there is open orientation on the x-axis. So the orientation is, well, horizontal, but it opens around the x-axis, let's put it that way. So we want to try to draw a vase that opens up on this side, right? So it's going through the origin because 0, 0, 0 makes that. And then it's kind of opening up out here. And it's an ellipse. So what's happening is you have this kind of bowl shape coming back, right, from the origin, like that. And again, as per usual, it's so much better to look at it in Maple. So I have it in Maple. It's right here. See, it's kind of a vase shape. Right there it is. Or a cone. I mean, it's not really a cone, though. It makes me think of like a megaphone, but it's a vase or a bowl. But it's opening up in the x direction, the positive x direction. I guess I should say the positive x direction, opens up around the positive x-axis. All right. Well, this video is getting a little long, and this is going to require completing the square. So how about I do that at the start of the next one?